Want to take a look at some of the other parts of the mosaic, because remember we said pieces of a mosaic are different because it helps make the big picture. It helps finish the picture and helps the picture fulfill its purpose.
Did you get that picture from our
I did. It is in your textbook.
We didn't talk about the integral membrane proteins in the third field.
You are correct. We have not. They are our last three parts, two of three actually, that we need to talk about in this picture. Integral membrane proteins that you will see right here have another name. The other name we have for them is transmembrane proteins. Transmembrane proteins. We call them that because they go across the entire membrane. So like a transcontinental flight flies from New York to LA, a transmembrane protein spans from the outside all the way in, which you can see here. It's on the outside, the extracellular side, all the way to the inside, the intracellular side. So it's transmembrane. Certain kinds of transmembrane proteins are also called carrier proteins. They're the ones that have a hole in the center of them, like this one does that got cut in half. It's got a hole in the middle of it, and that's called a carrier protein. Our transmembrane proteins, yep. Well, that's just the name of them so far. Our transmembrane proteins embed in a very specific way. The top and bottom of those proteins are polar, and they kind of nestle up against those glycerol polar heads.
What was it called?
Transmembrane or carrier.
Okay.
So the inside and outside of the protein, the stuff that touches the surface of the cell is polar, and the stuff that touches the fatty acids, that's all nonpolar. It's not a surprise that like things hang out with like. So things that have similarities would rather spend time with things that have other things in common with it. Just like you guys do, it is quite likely that some of the people that compose your friend group is because you have things in common. You have common likes, interests, dislikes, sports, etc. Their job, being embedded in the membrane like this, is to allow molecules that can't freely pass the membrane to have a passage. So I'll compare a carrier protein to a dog door on a screen door. The purpose of the door is to prevent really big things from going in and out. But your dog needs to go in and out at will. If it has to go to the bathroom, you certainly want it to go out the dog door and do that outside rather than inside. That's the function here of these transmembrane proteins. They allow larger things that can't fit between the phospholipids to pass through the membrane. So they're a larger gate or a dog door or a hole, but not the kind of hole that's going to get bigger and cause the whole membrane to fall apart. That would be bad. The other kind of protein here is embedded on the surface, and we call them peripheral proteins. You've heard the word peripheral before, most likely in reference to peripheral vision, the vision that's all the way on the side of your head. That's because peripheral proteins are attached on only one side of the cell. They're on the outside of the cell. Well, some of them are on the inside. But they're only on one side. So this pink one is not the same as this green one. They are different proteins and attach only on the surface. They have a variety of different functions depending where inside or outside of the cell they are. Some of them are used as chemical messengers to communicate with other cells. So it depends where they occur. The last thing embedded on the surface is only on the outside here. It's these green squiggles. Those carbohydrates, they act as a name tag. They basically say, hello, my name is, and identify that cell to any other cell that it meets. That's one way your body recognizes foreign invaders. It looks for the carbohydrates on the outside of the cell, and it's like, whoa, that's not one of me. I should eat it or destroy it or it's going to make me sick.
Could the carbohydrates like be copied instead of never mind, I'm sorry. That was a bad question. I didn't take that
Well, that kind of made sense.
for once.
So,
Michael, why don't you be a friend? So mean. Why don't you be a friend?
whoa, whoa,
Name him.
we clearly didn't pray. Whoa.
Oh yeah, that's true. I want 3 compliments.
Oh, yeah.
What would possess you to say that on a day that I clearly already yelled at you guys for behavior?
He has 2 classes with me, so I mean he's getting his.
Oh, I got 2 classes too.
Yeah.
And as we talk about this kind of movement across cell membranes, why things go in and out of cells, I'm going to use one of my favorite examples because it is one that annoys the living bejesus out of me. There are certain stores in the mall I don't go in. They're not meant for people my age, so you can imagine I avoid them. These kinds of stores are like Hollister, Abercrombie and Fitch, not intended for people my age. So I don't go in them because, well, there's nothing there for me to purchase, and their sales associates are tasked with doing something that just is an assault on one's senses. One of the things that the parent company, whether, I don't know if you guys know this or not, they're owned by the same parent company. And their parent company has all of their associates for any of their stores with signature fragrances, take the signature fragrance to the mall corridor outside of the mall and spray it. You ever notice how when you go by those stores, they reek to high heaven? The reason for that is because they're actually, hourly, there is an employee who takes their cologne or perfume or body spray and sprays it outside the store to try and attract people to it. No joke. I did not work there. But if you stick around any mall long enough, you'll see those people go out. It is practice of that parent company to do so. They do the same thing at Bath and Body Works. Yes.
It's kind of.
And Bath and Body Works and White Barn, you would think it just kind of like pours out the doors anyway. So they do this, and you know that you're getting progressively closer to either of those stores because the smell gets stronger. But you can smell it from really far away in the mall, right? So you could be at the food court and you're like, for the love of everything holy, is that necessary? Just want to eat like my cheese curds and my coney dog from the A&W in peace.
They should do it in the bathroom. They should like spray it all in the bathrooms.
I would prefer people just not spray things at the
What
mall.
if they like left them in the bathroom? Just like.
But here's the thing. You guys understand what happens when the employee goes out and they squirt the aerosolized scent. What happens?
We attract.
You're infecting the cells. Wait, that makes sense.
Think about the smell. What happens to the smell?
It goes away.
It disperses. And the reason it does that is because it's aerosolized. It's a molecule, right? It's a whole bunch of molecules. And molecules are always in motion. Whether they are solids, liquids, or gases, they're always moving.
Are those like the fragrances that you spray? Do they destroy the ozone layer? Or is that just more like air?
Only if it's in a certain kind of canister. So only if it's in,
Like a metal?
you know the kinds you can't puncture because they'll explode? Yeah, that kind.
Have you ever tried puncturing?
No, I'm petrified of explosions. The idea of something like shrapnel in general sounds bad to me.
You know there's a camper that lets you shoot those with guns?
I will say,
Someone just went out into the woods and like.
oh no, I would not. I shrapnel. I'm a risk rewards person. Like I evaluate the risk versus the potential reward, and if the risk outweighs the reward, I don't engage in the behavior.
But it's an explosion. That's pretty cool.
Yeah, you know, at camp,
So in the movie Jaws, could that actually happen?
At a summer camp I went to in
So-
Florida, like they let you bring your own X cans to the gun range to shoot.
So you understand. So you understand the idea that these molecules are always in motion. And when they're in motion, if two molecules run into each other, what direction do they go?
Opposite.
Opposite direction until
They hit another object.
they hit another object, and then
They bounce again.
and they continue to do this until they're farther and farther and farther apart, right? That process is a natural chemical process we call diffusion. And it's when things move from an area of high concentration, where they're very close together and constantly bouncing off of each other, to an area of low concentration. And they'll do that until we reach what we call equilibrium, until the concentration is even across a space. And then the employees of Hollister are tasked with going back out, making a new concentration gradient of high concentration, so that will continue to disperse down the concentration gradient. And that's how they assault all of our nasal passages. I wish they'd stop doing that.
I wish people would say that more often. My nasal cavity. Because
You're
it's
salty.
sensitive.
You're salty.
Now you guys can say it.
You're just salty.
When we talk about diffusion moving from high concentration to low concentration, we call it moving down the concentration gradient. And what I typically do is compare it to what happens to if you had an inclined plane, Reed Hill, and you put a ball at the top of it, what happens to the ball quite naturally? Down the inclined plane until it reaches a level surface and then stops. Diffusion is going to be the same thing. Diffusion is going to be molecules are going to move from high to low, naturally, no energy required. This requires no energy at all. It just happens until it reaches equilibrium, and then it stops.
Wait, what is, you said it's what gradient?
Concentration. So it's moving down the concentration gradient. When the molecule doing the diffusing is water, we call it osmosis. So osmosis is just a fancy term for the diffusion of water from an area of high concentration of water to low concentration of water. Now,
Sorry.
Yep.
Does that ever go the other way from the
not passively, not without energy. So for example, when large things have to pass the membrane to move from high concentration to low concentration, that's when they use those carrier proteins. They can pass freely through carrier proteins, no big deal. We call that facilitated diffusion because we helped it. We gave it a passageway. So facilitated,
a friend?
yeah. So you didn't have to walk amongst the seniors alone.
Wait, no, so it's, no, or it's kind of like the senior who likes freshmen. That, like,
No, or it's kind of feels like a bridge over them.
I have a feeling that we're gonna be doing
When does that happen?
That is so
I don't know, I'm not really sorry.
Actually, no, we have a lot of.
So every time we've talked about crossing the membrane so far, we've talked about crossing the membrane and not using any energy to do so. Whenever you cross the membrane and you don't use energy, it's called passive transport.
Can you repeat that?
When molecules cross the membrane and don't use any energy, we call it passive transport. So passive transport is diffusion, osmosis, and facilitated diffusion. Those are all three types of passive transport.
So what's that carrier protein called?
Here's my cell, right? I have a cell, it has an inside, it has an outside. If I have 10 water molecules inside and 2 water molecules outside, if water is going to cross the membrane, so there's an equilibrium or equal concentrations, what way is water going to move through the membrane? Outside until what?
Until they're equal amount of H2O.
Until there's equal amounts of water on the inside and outside.